This video is a tutorial on ratio and proportion, and what I'm going to look at specifically here is inverse proportionality. Okay, so first of all, let's just think of a simple ratio. So let's have 3 to 5 then. 3 to 5, so nice easy numbers. If I was to think of what the proportion of 3 to 5 would look like on a graph, as we saw in the last video, then if I draw it on some x and y axes, let's label this x then, and label this y. So this 3 now refers to the x value and the 5 refers to the y. Then if I number this up, so 5, 10, just a couple of numberings just to get us started here, and we'll go up to 15. Okay, 15. Alright, so now as we saw in the last video, what we can do here is plot this on our graph. So we've got 3 to 5, and if we were asked about if we had 6 to question mark, we would say, okay, well, probably if I double this, okay, so this is times 2, then I'm going to double this. Okay, so that will be times 2 as well. So we'd end up with 6 to 10. Okay, so we've got 6 to 10. And if I draw a straight line between these 2 points here and draw it back to the origin, one of the things we discovered in the last video was that we can, if we know about linear equations, we know this is y equals some constant k, which is the slope, times x plus the intercept c. Well, that's going to be 0 with a directly proportional graph. So we can just remove it, and we end up with this idea here. In other words, that when y is directly proportional to x, or we usually write it the other way around, x is directly proportional to y, means the same thing. We can rewrite that y equals a constant, which we call the constant of proportionality, times x. And from there, we can just plug in our values to get any value that we want. So in this case, we would plug in the 5 and plug in the 3. We would get the value of k, the constant of proportionality, in this case as 5. So that's the rise over the run, 5/3. Now all this breaks down when you've got inverse proportionality. Okay, so when we've got inverse proportionality, k is not going to equal 5/3 at all, so let's just erase that. And x is inversely proportional to y. In other words, x is proportional in this way, 1 over y. Okay, let's just have a look now at what that means, and let's have a look at an example of this kind of inverse relationship. Okay, so we need to erase this now and give ourselves this example. All right, so I've got now 3 monkeys. Let's get back to here. I've got 3 monkeys, and we're saying that it takes our 3 monkeys 5 days to solve this problem. Okay, 5 days to solve the problem. So if it takes 3 monkeys 5 days to solve a problem, how many days would it take for our 6 monkeys? So 6 here. 1, 2, 3, 4, 5, 6. Well, if it was a directly proportional problem, then our answer would be 10. But clearly 6 monkeys are going to do the job twice as fast as our 3 monkeys here. So it's not going to be 10, it's going to be half of 5, which is going to be 2.5. It's going to be quicker, so it's going to be 2.5 days. So in other words, we'll end up with 6 to 2.5 or 2.5. Now, what I want to do is just graph this to show you the difference. Okay, so whereas we had a simple straight line graph, a linear equation for y is directly proportional to x, we're going to have something very different here. Okay, let's get rid of our monkeys now and have a look at the graph of this inverse relationship. Alright, so we have to now erase this because we know this is wrong, and we can let's just draw this on now correctly. So 6 and 2.5, so that would be about there. So we've got a couple of values here. Now to get the other values, I'm just going to draw a t-table and consider 1 to 9 or 1 to 10. Let's just draw a t-table to start with. So if you just, a t-table is when you simply draw down and across. So it's called a t-table, I guess, because it's a bit like a T. Okay. So the t-table gathers up our x and y values, and then we plot from the t-table onto the graph. So if we think about, let's just number this 1, 2, 3, 4, 5, 6, 7, 8. Okay, we'll stop there. 9. And down here, 7, 8, 9. Okay, so there are our values on our graph. Let's just neaten up that 6 there. Okay. Right, now we've got values for 3 and 6 already plotted. So 3 is when x is 3, y is 5. When x is 6, y is 2.5. So I'm going to write that 5 over 2. Okay. Now, what about when x is 9 then? So when x is 9, what would that be? Well, that will be a third of 5, okay? Because this value has gone up, yeah, to get to 9, that's gone up by how many? 3. So in other words, it's trebled. So this value here, inversely, is going to multiply by 1/3, so 1 over 3, okay? So a third of 5 is going to be 5 over 3. And that makes sense, doesn't it? We've got 5, if you like, over 1 here, 5 over 2, and 5 over 3. Okay, let's go back to the start of our table now and think about 1. Now to get down to 1, what would have happened to that 3? Well, instead of times 3, it's going to be times a third. It's going to be a third of that 3. A third of 3 is 1. So if it's a third on this side, it's inversely proportional, so this goes up by how much? So the inverse of a third is 3. So it's times 3. Times 3 then. So 5 times 3, 15. And does that make sense? If there's only one little monkey, then that poor little monkey is going to take much longer. So it takes that monkey 15 days. 3 of those monkeys only takes 5 days. And that makes sense, doesn't it? In other words, that's 15 has come down a third of 15 to get to that 5. And that's because there were 3 monkeys. So we seem to have everything all right so far. Let's now consider 2. What if I just erase this, what if I take that 3 down now, to 2, what have I done? I've multiplied by 2/3. So 2/3 of 3 must be 2. Okay, so if it's 2/3 on that side, what's it going to be on this side? Times 3/2. So we just invert the numerator and the denominator. So we've got 3/2. So that 5 now is multiplied by 3/2. So multiplying 5 times 3 gets 15 divided by 2. So 15, whoops, wrong column. Okay. So 15 halves, if you like. Okay? Now, what about 4? That's going to be 4/3 and 3/4. Okay, so in the 4 column, let's just make that 4 a little neater. In that 4 column now, I've got 5 times 3 is 15 divided by 4. So 15/4, or 1/4 of 15. And you might be able to see a pattern here so that you could fill in the rest very easily. But let's just work it through in the same way. So we've got 5/3 becomes 3/5. So 5 times 3 is 15 divided by 5. Okay. Now, if you haven't seen the pattern so far, let's just adjust these figures here. So instead of 5, I'm just going to scale up. So that fraction becomes 15. Okay, so we want it to be 5, so 15 divided by 3. Okay, this becomes 15 divided by 1. And this becomes 15 divided by, so scaled up by 3, 6. And now we can see this pattern. 1, 2, 3, 4, 5, 6, 7, 8. Okay? And this could be expressed as 9 if you like. So 15/9. So now we can plot these values on our graph. Let's start at 1. 1 along then, and 15 up. Let's just erase our workings here. There we go. So 1 along and 15 up gives us our first plot. 1 along and 2 along and 7.5 up gives us our second plot. We've already done 3 along and 5 up. 4 along then, and 15 divided by 4. Well, 4 goes into 15 3 times, 3 remainder, so 3 3/4. So 4 along, 3 3/4 up will take us to here. Okay. 5. Well, 5 into 15 goes 3, so that's exactly 3. So that's interesting. The 3 to 5 has become 5 to 3. Here we've got 6 to 2.5, which we've already done. 7 into 15 goes 2 and 1 remainder, so it's going to be 2 1/7 up. That's about there, just above that line there. And then we've got 8 into 15, well that's just 1 and 7 remainder, so 1 7/8. So that's going to be just under the line there. And then finally our 15 divided by 9, so that's 1, what was that? Originally that was 5/3, wasn't it? So if I think about it like that, that's going to be 1 2/3. Okay, 1 2/3. So that's about there. Okay, so you should now be able to see what we've got. Instead of a straight line, if I join these points up carefully, there we've got a nice curve, and that's a y equals 1/x function, is the function, and that gives us this lovely curve Okay, and so that curve is the curve of the inverse proportional relationship. Okay, now having worked that through, let's see if with just that bit of knowledge we can solve some problems. So let's say we had, for example, well, let's just use this problem that we had here. So let's call it problem A. So we've got 3 to 5. 3 to 5 is inversely proportional. So we'll say inversely proportional. Inversely proportional. So all these problems would be inversely proportional. So we'll now have 18 to, let's call it y. Okay, and we need to find y. So if it's inversely proportional, then y, so therefore y equals our constant of proportionality times 1 over x. Okay? And a better way of writing that, in fact, is just to multiply that 1 by the k. So we get k. Oops, is that clear? K over x. There we go. So just as before, we want to find k. How do we find k? Well, if we do a little bit of rearranging here, it's slightly more difficult than it was before, but we should be able to rearrange this quite easily. So if we multiply both sides by x, then that will disappear from the denominator. So if we multiply the right-hand side by x, we just get k. If we multiply the left-hand side by x, we get xy. Therefore, k equals x times y. Okay, so just rearranging that equation there to give us a simple formula for k. K is x times y. So it's sort of easier than direct proportion in that all we need to do now is multiply the x and y. So if k is x times y, then k must equal, so k equals 3 times 5 equals 15. And now if we go back to our original formula, so now we've got so therefore y equals k, which is 15, divided by x, and subbing these values in here then, so 18, we end up with y equals 15 divided by 18, which we can simplify to 3, both divisible by 3, so 15 divided by 3 is 5, and 18 divided by 3 is 6. So we've got our value for y. Y is 5/6. Okay, when x is 18, so that would be way up here, we've now, our curve has come down to about here. So let's get this right. 18, so that's going to be 11, 12, 13, 14, 15, 16, 17, 18, and we've got 5, 6, which is about there. So it looks about right. So without graphing it, we can be fairly confident about our answer here. Another way of checking it is if you use the same sort of checking method, we can actually use a fraction method here, where if you take this value here, and so we just do a little check here, if you take this value here and put it over this value here, 5, and then take this value here now and go in the opposite direction, and that's very important. This is because it's an inverse relationship. So 3/18, we should get the same answer. Let's try. So cross multiplying, we get y equals 3 times 5, so 5 times 3, which is 15, divided by 18, so 5/6. So good. Simple check means we can confirm that this must be correct. Okay, let's try another one. So, problem B. Let's keep the numbers simple so you can see very clearly what's going on. Let's try a 4:1 ratio. 4:1, but again, inversely proportional. So 4:1, and now let's have 2 to y. Okay, so what's y? Well, again, we've got this idea of y equals k over x, and we can rearrange that to get k equals x, y. So now k equals what? 4 times 1. K is simply 4. Therefore, y equals, going back to this formula here, y equals k, which is 4, over x, which is 2. So y simply equals 2. Okay? And does that make sense? Yeah. This halved, so this doubled, so y became 2. Simple check should again confirm that we've got the right answer. So let's just check. So we've got y, so again, if you think about it in this way, y over 1, so just y, equals 4, there we go, 4 over 2, equals 2. So we'll say that's correct. Okay, let's just finally increase the numbers a little to see if we can do slightly more difficult problems. What should we have? Let's have 2 to 19. Okay, is the same as, now what I'm going to do here is put x as the unknown and use a decimal, so 0.5. So y equals k over x, and rearranged we get k equals xy. So k equals 2 times 19, which is 38. Therefore, y equals what? Well, going back to this formula here, y equals k, which is 38, divided by x, which is, at the moment, just x. We don't know what that is. But we can now substitute in 0.5. So we now get, let's do it over here, 0.5 equals 38x. Okay, now how do we get the value for x then? So if we multiply both sides by x, we'll end up with, and change that from 0.5 to half, we'll end up with half x equaling 38. So x must equal half now. So multiplying by x, so dividing by half, so 38 divided by a half is the same as 38 times 2. So 38 times 2 is 76. Okay, so we've got our value for x, and does that make sense? Well, this was 19, it went down, it not only divided by 19, it went down right down to a half, So we would expect this to go up not just to 38, which is 19 times 2, but also up to 76 because of this half relationship. So it makes sense. We think we've got the right answer, but let's check using the method that we used before. But this time, slightly different. Well, we could do it in the same way. So we would end up with, if I write check, we'd end up with x over 2 equaling, and then we must go this way to check because it's inverse, so 19 over 0.5, and that will work out quite nicely. So x equals 38 divided by 0.5, which is 76. Another way of doing it, but I would urge a little bit of caution here, is that we might want to change these values. So whenever we've got a decimal, very often we want to change the values. So we could say, I don't want 0.5 anymore, I want this to be 1. So double it up to get 1. Okay, if I double that up, I can't though double this up. It's because it's not that kind of relationship, it's an inverse relationship. So I would have to halve, if I double this, I would have to halve this. So you can do this, but just be careful that you're still working inversely when you change any of these ratios. So now what have we got? We've got half x divided by 2 equals 19 over 1. So really it hasn't made life a lot easier, but let's work it through. Half x then multiplied by 2 must equal 38, and so multiplied by half becomes dividing by a half, in other words multiplied by 2, so we've got 38 divided by times 2 is 76. So we say that this must be correct. Okay, so lastly in this video I just want to introduce a couple of other relationships that are proportional. In fact, one way of thinking about this is if we look at this idea first of all of direct proportionality, where we have y is directly proportional to x, in terms of an index of 1. Now if we have an index of 1, that just means x, okay? So y is directly proportional to x. Y is directly proportional to x is the same as y equals constant of proportionality times x. And so why have I put this on here? Well, because if we don't have a directly proportional relationship, as we've seen, we'll have y equals the constant of proportionality times 1 over x. Well, 1 over x can be expressed as x to the minus 1, like that. So we now have two proportional relationships. We have the one which is directly proportional, so we say this is a directly proportional relationship, and we say this one is inverse or inversely proportional. But what if I change this now to a different value? Let's increase it to 2. Okay, now we would say y is squarely proportional to x. So we have the constant of proportionality again, we have x squared, and there's several examples of this in physics. If you think of area, if you think of light being cast on something, for example, you would get this squarely proportional relationship where you're interested now in the relationship, in the x value squaring while the y value simply works in a linear way. It just goes up normally. Okay, but both sides of this proportional relationship go up. It's just that this goes up a lot quicker than this does. You could have a cubic relationship. So this could be 3, and in that case you would have y equals the constant of proportionality times the cube of x. So these are two new types of relationship, but they work in the same sort of way. As long as you understand what the formula is going to be, then you can calculate just using that formula in exactly the method that we've used in the last video. Now, what if we think about negatives? Okay, so this time what I'm going to do is, instead of -1, let's change this to a 2. What would that mean? Well, that would be an inverse square. So the constant of proportionality and -2 is going to be the same as y equals the constant of proportionality over 1 over x squared. So that would be what that means. So negative, in the laws of indices, the negative means 1 over. So it's just 1 over x squared. Okay, so we would call that inverse square, an inverse square proportionality. And of course we can also have an inverse cubed. So let's just write this down here. Y equals the constant of proportionality inverse cubed, and oops, there we go, cube. And of course this could go up and up. In other words, what you've got in general terms, up and up or down and down, you've got this kind of format. So y equals k, the constant of proportionality. In fact, let's write that down because I keep saying it and it's obviously worth remembering. So let's write it down. So we call this the constant of proportionality. Okay, rather grand title, but an important constant, so that's why it's got a name. And here, what I've done is, oops, there we go. For this, I'm just calling this alpha to stand for any what? Any integer. So of course, if it's positive, so if it's a positive integer, that will be a direct relationship or a square relationship. If it's negative, it will be an inverse, an ordinary inverse, square inverse, a cube inverse, or going up again. So these are all the different types of relationship you're going to get, but the important distinction is between direct and inverse proportionality.